Hello everybody. So we are still in the introduction, and we are discussing now a very important parameter or term that we are going to be using a lot. It's going to be a very basic parameter that we are going to use in the coming parts of the chapter regarding the mass balance calculations for reactive system. And this is the extent of reaction. So extent of reaction is given a symbol xi. If you look at this, this is the symbol xi. It's a weird symbol, but this is the symbol that the textbook uses for the extent of reaction. So this is what we are going to use. So it is a parameter that we use to measure how far the reaction proceeded or continued, and it is defined as the moles reacted divided by the stoichiometric coefficient. So the word moles reacted is not very accurate. It is the number of moles. It's Ni minus Ni node. Ni node is the initial number of moles, and Ni is the final number of moles. So it is the final number of moles minus the initial number of moles, or the number of moles in the product minus the number of moles in the feed, divided by the stoichiometric coefficient. Okay, and this equation can be rearranged to be Ni equals Ni node plus the extent of reaction multiplied by the stoichiometric coefficient. So the product, number of moles of the product, can be calculated as the number of moles of the reactant plus the coefficient multiplied by the extent of reaction. The extent of reaction has two main advantages over the conversion when we express the how far the reaction proceeded. The first is that we can apply this equation to the reactants and to the products. So it can be applied to both. The fractional conversion can be only applied to the reactants. We cannot calculate the fractional conversion of a product. So this is the first thing. And the reason is this is the extent of reaction. It's not for the conversion of a reactant, and this makes a lot of sense. The second thing, that the extent of reaction is constant for a given reaction, meaning that it doesn't depend on the component. So, for example, if we have the same example that we solved last time, where we have ethylene plus hydrogen to produce ethane, and we have the feed was 20 kilomoles, 50 kilomoles, and 50 kilomoles, and we said 30 kilomoles were reacted or were consumed, and these 30 kilomoles reacted with 15 kilomoles of ethylene, producing 15 kilomoles of ethane, and then the product was 5 kilomoles of ethylene, 20 kilomoles of hydrogen, and 65 kilomoles of ethane. So this is the same example that we did. There is nothing new till now. So what we want to do now is to calculate the extent of reaction, and we will do this for the three components. Again, the extent of reaction is the final or the product number of moles minus the feed number of moles divided by the stoichiometric coefficient. So if we do the calculations for ethylene, it's going to be the final, which is 5 minus 20. This is the final minus initial, or the feed, the product minus feed, divided by the coefficient. There is a very important thing that we need to keep in mind here, which is that the stoichiometric coefficient, there's something we mentioned about the stoichiometric coefficient in the beginning of this part, which is that the sign of the coefficient. The stoichiometric coefficient is negative for reactants and positive for products, and here it's going to be very important. So when we do the calculations, it's going to be 5 minus 20 over negative 1. Okay, so it's negative 1 because it's a reactant. Here for hydrogen, it's 20 minus 50 over negative 2. For ethane, it's 65 minus 50 over positive 1. And all of them are equal. So it's going to be 15. So this is a very good thing about the extent of reaction, is that you calculate it for one component and you can use it for the rest of the components. So you calculate it once and for all, and this is going to be one of the key parameters that we use to calculate or do the mass balance calculations on reaction or reactive system. So if you can calculate the extent of reaction, you are I would say 90% done with everything, because the rest is going to be substituting in an equation like this, and we'll see this later. But I just want to make it clear that this parameter is a very important parameter. So let's look at this example here, where we have ethylene oxide produced by the reaction of ethylene and oxygen, and that the feed to the reactor is 100 kilomoles of ethylene and 100 kilomoles of oxygen, and the reaction proceeds to a point where 60 kilomoles of oxygen is left. So what we can do, because again it's not easy to understand the numbers. Now we need to calculate the fractional conversion of both and the extent of reaction. So one thing that we used to do is to put the table where we put the reactor, the feed, the reacting, what is reacted and produced, and the product. So in this case, we first need to adjust make sure that the balance is correct of the equation. So in this case, we have one or two oxygen atoms in and one out. So either to multiply this by half, it's half oxygen, or 2 ethylene and 2 ethylene oxide. So this is what I did here. So now the feed is 100 and 100. And we know that 60 kilomoles of oxygen is left. So I don't know how much of any of them reacted, but what I know is that the product is 60. And when the product is 60, we can now calculate the rest. So I know that the 60 means that the reaction started with 100 moles of oxygen, 60 left, so the reacted are 40. And since they are 40 moles that reacted, then they reacted with 2 over 1 times 40, so it's going to be 80, producing 80 moles of ethylene oxide. And now 100 minus 80 is 20, and 0 plus 80 is 80. So I calculated all the number of moles that I have here, and I can calculate the requirements. The fractional conversion of C2H2, it's going to be in minus out over N, so 100 minus 20 over 100, which is 0.8 or 80%. For oxygen, 100 minus 60 over 100, which is going to be 40%. And the extent of reaction can be calculated for the reaction given any one of the numbers, or using any one of the numbers that we have for ethylene, for oxygen, for ethylene oxide. It doesn't matter. So for ethylene, it is going to be 20 minus 100 over negative 2. For oxygen, 60 minus 100 over negative 1. For ethylene oxide, 80 minus 0 over positive 2. For the three cases, it's going to be 40. So this is one solution that we did, or we can do. And this is fine. However, we don't like to put these tables and list all the numbers in the table for many reasons. One of them is that if we have multiple reactions, it's going to be very difficult, and we will see this shortly in 2 or 3 videos. When we deal with multiple reactions, it's going to be very hectic. So we can use equations instead. Meaning that we can solve the problem without doing all this table and all these things. And we can do this by listing the equation and putting all the parameters that we have as parameters. So I have here the number of moles of C2H4N is 100, which is this. And for oxygen, it is 100 as well. For oxygen out, it is 60. This is what we were told, that 60 are left. And we put here the stoichiometric coefficients, which are part of the solution. And now, given the information that we have, we can calculate everything by using the information that we have, by starting with the extent of reaction. So again, we said the extent of reaction doesn't depend on which component, it's the same for all of them. So if I calculate it using any one of the components, I can use it for the rest of them. So I know the number of moles in and out for oxygen and the coefficient of oxygen, which are all the information I need to get the extent of reaction. So it's going to be 60 minus 100 over negative 1. So this is the extent of reaction. Now I can use the same equation to calculate the product, the number of moles produced for ethane, which is N out equals N in plus the coefficient multiplied by the extent of reaction. So it's 100 plus negative 2, which is minus 2, multiplied by 40, so it's 20. And the same if you want to calculate the number of moles of C2H4, it's going to be, or mean ethylene oxide, it's going to be possible, but it's not required here. That's why I didn't calculate it. But the fractional conversion is going to be the same, n minus out over n for ethylene oxide, and for oxygen it's the same. So this solution, as you see, didn't require a lot of steps and a lot of calculations. I just put the equations and substituted in them, and again they are all about this. And again, the balance equation here that we see here, it is a relation between the product and the feed, which is something that we need a lot when we do mass balance. So if you have a reactor, you have feed in and the product out, you need to calculate the product in terms of the feed, and this is what this equation is helping us with. So we'll stop here and continue next time, inshallah. So I'll see you then.